Hello, my name is David Hemrick and I am a student in Everything is the Same, and this is my video for the week 8 demonstration. And so we're going to talk first about the electrical diffusion circuit that we built, and then I have a little demonstration about the diffusion of heat. So here's the circuit built on a breadboard. Mine was a little smaller than the one that was on the parts list. I had it already, so it's pretty packed in there, but the design is the same. It's got the LEDs there and resistors and capacitors, and here's the big capacitor, and we're going to charge that up. Long lead to the positive terminal and the short lead to the other. A couple of seconds, and that should do. And now I'm going to very gingerly, hopefully to holding this where you can see it, put that in the circuit, and there they go. They light up from the center, and then the current moves out to the edges. So that, and then of course they fade over time, which I guess is because it's not a perfect device and the current leaks. So that's electrical diffusion, and we studied the equations that govern that. Now the next part, I'm going to demonstrate some heat diffusion, and we're going to use some things in the kitchen. And the first one we're going to use is this cast iron skillet. This is an 8-inch Lodge skillet, and it weighs about 5 pounds, and it's made from a material called gray cast iron. And what I'm going to do is I'm going to put that on a heat source that I'm going to talk about, and I'm going to put some little pieces of a birthday candle like this, and I'm going to place those on the pan from the center out, and we're going to put it on the heat source, and then we're going to time how long it takes to see those pieces of candles start to melt. And I'm assuming that that material is pretty uniform and that they will melt at about the same temperature, and that's not too outrageous. I think these are pretty uniform candles. And I might note that sometimes people who work in iron foundries use engineered wax crayons to measure, for example, the temperature of a casting when it's being handled in the foundry, moved around the foundry. If they don't want to do certain steps before it's cooled off to a certain temperature or above a certain temperature, so then you can take a little crayon that melts at a known temperature and draw that on the surface of the casting, and if it melts, then you know it's hotter than that temperature, and then you can select from another one in the set, and you can kind of bracket that temperature. So the idea of using a wax material to melt and indicate temperature is not a new one. So I'm going to show that in a couple minutes while we set up. Okay, well here we are in the kitchen, and we've done our little setup, and we're going to use this kitchen stove, and here it is, the cooktop. That is a 6-inch diameter burner, and it's set on high so it doesn't cycle. And there's our pan, 8-inch pan. It's 8 inches across, skillet. It's 8 inches across the bottom, and there's little pieces. They're all about a 1/4 inch long, kind of about the same size, and they go from the center out to the edge in the pan. And what I predict is that the first 2 or 3 on the inside will melt all at about the same time, and then the ones toward the edge will take progressively longer, because it's a circular item, so it's heating. We're trying to heat a greater volume as we go out from the center to the edge, and there's probably might even be some other reasons as far as how heat transfers through that solid, why it would take longer and longer. So anyway, here we go. I'm going to put that pan on that heat source, and I'm going to do the best I can to center it, and I think because of the features of the pan I can do it pretty well. Okay, so now it's on there, and we're just going to watch that, and I'm filming that, and I'm going to look at my, so the one about this, the middle one actually started first, so the first 3 are all gone, and they're melting. They all started to melt about the same time. Now the next one to the edge is gone, and now we're waiting on the one farthest away. And we're waiting, and they're going to start to smoke, and I still haven't seen it do anything. Let's get in there and watch it. A little too close. Let's back up a little bit. It's smoking and smoking, and the other ones are pretty hot, and I'm still looking pretty closely at it, and it hasn't gone yet. And waiting and waiting. Okay, and there it goes. So I'm going to say it flowed there finally. I'm going to take that off the heat and turn it off, and maybe put the fan on in a minute after I'm done talking. So anyway, that's kind of the that's the setup with the iron pan, and then I'm going to do that with a pan from a different material, an aluminum pan, and we're going to see how that behaves a little differently, and so we're going to do that again in a minute. Okay, so now we're going to do the this same experiment, and what I've got this time is a Tefal aluminum pan. I confirmed that that was aluminum by seeing if a magnet would stick to it, and it won't. And it's lighter than the other one. It weighs about a little less than 2 pounds, and it's thinner, and as I said, it's made of aluminum. It's also 9 inches in diameter, so I have placed my little piece of my little candle indicators at the same, as close as I can get, coordinates, from the center, and then at 1 inch intervals out from there. It doesn't go quite to the edge because this pan diameter is 1 inch larger than the other one. But we got our heat source going again, and I'm going to put this pan on there with our little indicators, and this one I have to work a little harder to center it, and I'm going to say that's it. So there we go, and let's get in on that. And my prediction about this one is it's going to behave similarly to the iron pan, except that I think the heat is going to transfer faster through the thinner. Okay, so there's the first two. They're gone now. They've melted now. And there's the third one. And well, the fourth one, if you look at it, you can see it's really already started. So that one's done. And now we're waiting on the fifth one. And I don't know, like I said, my prediction is we don't have to wait as long as we did on the heavy cast iron pan. This pan also has a non-stick coating on it. I don't really know what that material is exactly, on what it's I don't know too much about what the heat transfer properties are. And there goes the last one. Now it's melted too on the edge. So that did not, I don't think, take as long as the first one. We'll time all that out and go through some of our data on that. Okay, well, I got about a minute left, and I find that as I look at the data that I got from timing out the video, that up until the last position, 4 inches from the center, the times were very similar. 11 seconds for the iron pan for the first three, 12 seconds for the aluminum pan, and then for the first two, and then the 15 seconds, then they were the same to the 3 inches out, and then the big difference between the 3 inch and 4 inch position, much slower heating up for the iron pan, quicker for the aluminum. That's not really what I expected to find. I'm wondering if maybe that the coating on the aluminum pan has something to do with that. But anyway, that's kind of interesting, and at least to me, and I hope you kind of enjoyed the demonstration of heat as diffusion. Thanks for watching, and congratulations on finishing Everything is the Same.